In this video, we'll look at using the parallelogram method for adding vectors. So we'll work through an example so you can see how this works. So the example is that a plane flies 200 kilometers south, 40 degrees east, then turns and flies 450 kilometers north, 20 degrees east. So our first question is to find the magnitude of the resultant vector. So we can do this by adding tip to tail, but we're going to use what's called the parallelogram method so you can see how that works this time around. So in order to do this, we're going to first draw the vectors. So let's start with our first vector. A plane flies 200 kilometers south, 40 degrees east. So if you need to, it might be worth jotting down what the compass coordinates are: north, east, south, and west. So this south 40 degrees east means we start going south, but then we head 40 degrees east. So that kind of looks something like this. And the angle in here would be 40 degrees. And then the plane turns and flies 450 kilometers north, 20 degrees east. So I could do that from here, just kind of like we've looked at before. I could try to figure out, well, north is kind of about here, 20 degrees east is kind of over here, so that I can line up my vectors tip to tail. Instead of doing that, though, I can go right back to the sort of center of our compass bearings and just do 450 degrees north, 20 degrees east from here. So north is here. We want to go 20 degrees off east, and that would be 450 kilometers. So this angle in here is 20 degrees. This length is 450 kilometers. I forgot to put a length down here. I'll put it over here just so we don't clutter up the diagram too much. And the way that the parallelogram method works is that we draw a parallelogram with these two vectors. So notice the vectors are joined at the tails this time. That's important for this parallelogram method to work. We have the vectors tail to tail, basically. And essentially what we do is we create a parallelogram. I'm just going to change my pen color. I want to create a line parallel to this one. It's hopefully somewhat parallel. So there's that line there, and we'll do the same thing over here. And then with this parallelogram method, the resultant vector, so the vector you get by adding these two vectors, is the vector that goes from where we started to the opposite corner of the parallelogram. So you can see we have a parallelogram, sort of looks like a parallelogram, and the vector that we're interested in, this resultant vector, goes from the center of the compass coordinates, or where we started our vectors, all the way to the opposite corner. So this is our resultant vector. Typically we use the letter R for resultant. Whoops. So we'll call that R, and I'll just remind you that's the resultant. So that's what we want to find. The nice thing here is that once we draw our diagram, this becomes all about trigonometry, essentially. So what we've done is we've drawn the vector. We have some lengths. So I didn't put these on, but maybe I should. This side length in our parallelogram, so the this one down here is 200 kilometers. The opposite side is also 200 kilometers. Whoops, not 20, but 200, pardon me. And then same here, that this side is going to be 450 kilometers. So we have a lot of side lengths. I should say a lot, but we have some side lengths. It would be helpful to have an angle somewhere in here. So let's go ahead and do that. Well, we know that this angle from here, I don't know, let's see, I'll just change my pen color one more time. We know that the angle, and I'll just draw it temporarily, the angle from here to here needs to be 180. It's a straight line. So that needs to be 180. So we have 20 degrees, we have 40 degrees. So let me just erase that line. So we know that this angle inside needs to be the supplement of that. So 20 and 40 is 60. That whole thing has to add to 180. So this section in black inside the parallelogram has to be 120 degrees. And then the other thing that's helpful to know, if you don't know this already, and you may not, but angles in parallelograms that are adjacent to each other, so side by side, have to be supplementary angles. And what that means is that angles that are side by side need to add to 180 degrees. So we have that this angle is 120. This angle right in here is 120, which means that the angle beside it, when we add together, we need to get 180. So this angle has to be 60, which means that this one also needs to be 60. And now, if you look at our parallelogram, we've essentially created a triangle with this resultant. That triangle, you can either do the one along the bottom, you can do the one along the top, it doesn't really matter, but we get a triangle in here. So we're going to go ahead and solve that triangle for the resultant. So we'll just maybe remind ourselves here. We'll just say let R represent the resultant. I know I drew it on the picture before, but helpful to write it down. So let R represent the resultant. And then we're trying to find the length of that vector. And so using this sort of triangle that's highlighted in red, you can see that we have two sides, one that's 200 kilometers, one that's 450 kilometers, and we're trying to find the third side. We have the angle in between, so we're going to just go ahead and use the cosine law here. So the cosine law is going to tell us that R squared, the magnitude of R squared, so these little bars just mean the magnitude. So the length of that vector R squared has to equal 200 squared, so this is just the cosine law, plus 450 squared, so the one side squared plus the other side, minus 2 times the first side, times the second side, cos of the angle opposite the side that we're trying to find. So we're trying to find this side length in our triangle. We have this angle here of 60 degrees. So we'll do the cos of 60 degrees. And so we can plug that all into our calculator, and we'll get that R squared, the magnitude of R squared, is equal to 152,500. And then we can take the square root of that to find the actual magnitude of the vector R. And the square root of that is approximately 390.5 kilometers. So that resultant vector then, to answer the first question, the magnitude of the resultant vector is 390.5 kilometers. Therefore, the magnitude of the resultant is 390.5 kilometers. All right, let's look at part B now. That was part A. Part B asks, find the angle between the vectors representing each part of the flight. I think we've already done that, right? So the angle between the two vectors, maybe I'll try to highlight in a slightly different color. Here's the one vector. Here's the other vector. The angle between them we've already figured out was 120. If you wanted to see that as a calculation, we took the 180, we subtracted the 20 degrees, and then we subtracted the 40. So the 20 degrees, that's right here, and the 40 degrees here. And we got 120 degrees. And then part C says to find the quadrant bearing of the resultant vector. So here's our resultant vector. This diagram's getting a little bit crowded, but hopefully we can make it work. What we want to do is we want to figure out what is this angle in here. Because then we can say it's north so many degrees east. So if we can find out this angle inside the triangle, and what I might do is just grab a screenshot of this not quite as cluttered. That will make our life a little bit easier. I'm a little bit worried that diagram's getting very cluttered. All right, here we are. So again, if we can find this angle theta inside the triangle, just highlight that a little bit better. If we can find this angle here, theta, and then we can just add 20 to it. Well, the nice thing is that we already have two sides, three sides in this triangle plus an angle. Remember, we just found this side here is 390.5. So we have three sides in the triangle, and we're trying to find an angle. So let's go ahead and use the sine law here. So I'll start by just saying find theta. So find theta. Theta is just that angle inside that red and blue triangle, nothing more. And so let's start with sine 60. We know that this angle here is 60. So we'll do the sine of 60 divided by the length of that opposite side, which is 390.5, the one we just calculated. Whoops. That has to equal sine theta divided by the opposite side to that, which is this 200. I'm going to multiply both sides by 200. We'll do 200 sine 60 over 390.5 is equal to sine theta. And now we just need to do the inverse sine of both sides to figure out what the answer is. I'll do that just before jumping to my calculator. Again, if you need to, you can enter this in steps. If you feel comfortable, you can do this all in one go on your calculator. Whatever is easiest for you. And that should equal theta. And if we plug that into the calculator, we should get that theta is equal to 26.3 degrees. Now remember, theta was just this part shown in green. If we're going to do a bearing, we need to either go from the north side or from the south side. We already know the angle up here is 20. So the bearing then is going to be north. 20 plus the 26, that's a total of 46.3 degrees. So we're 46.3 degrees off north in an easterly direction. So there's going to be our bearing. So that's how we can add two vectors instead of going tip to tail, without going tip to tail, but just using a parallelogram. So just a little bit of trigonometry, really.